So the following chapters that you will going to study, starting from today up till the following chapters, will be basically on the properties of a material. So in the material chemistry, we cannot run away with the application and also the properties of a material. And for today, we are going to look at one of the important chapter that normally you will have at least two questions. Remember, at least two questions in final exams, okay, for phase diagram. So probably when you heard about phase diagram, you will, I think, remember that what you have learned during your high school, during your A levels, during your STPM or matriculation about the phase diagram of water. You have a triple point and others. But what actually phase diagram indicate is that the, the phase or the composition of the material at the different temperature, at the different conditions. So things that we are going to address in this chapter, probably when you have two elements. Normally, this chapter we are going to address the phase diagram of an alloy or metals. So in order to produce alloys, you know that you will combine at least two elements to produce one alloy. So what will be happen to the physical state or the properties of this alloy? Okay, so what equilibrium state do we get, right? So in particular, if you are producing alloys at the different composition, like different percentage of copper, different percentage of nickel, then what will be the characteristic? Either it will exist as a liquid state in which temperature, either it will exist as a solid at which temperature, or if it will actually exist as a mixture of two solids at different temperature. So then in phase diagram, we can also identify how many phases that you will get in the end. Okay. And what will be the composition of each phases? So you will actually look into this, and finally, how much of each phases do we get? So as definition, phase diagram is basically a graphical presentation of the combination of temperature, pressure, composition, or variables for which specific phases exist at equilibrium. So it also explains what phases that will exist and what phases that will transform when we change the temperature, pressure, and also composition. So this is actually what I'm talking about to you just now. So we normally you have looked into this. Okay, this is actually a phase diagram of water. So at certain temperature, okay, below 0 degree, okay, water will be solidified. It will form ice. Okay, so this is actually ice. Okay, and then if you actually increase the temperature, or if it is actually beyond 0 degree, it will exist as liquid or water lah. Okay, and if the temperature exceed the critical point, the boiling temperature, the normal boiling temperature, then it will convert into gas or vapor. Okay, right. So this is actually the basic concept or the basic phase diagram of a normal water. But we are not going to study this. This actually level 100 lah kita cakap. Ini level budak-budak aja. So we are going to look at the phase diagram of an alloy. So still on the definition, what does it mean by phases? Fasa. It is actually a portion of a system that has distinct physical and chemical characteristic. So when we talk about phase, you know that phase actually exists either solid, liquid, gas, or whatsoever. So these phases actually has its own special characteristic gas, the distribution of the particles is different as compared with liquid and also with solid. So this is actually why what it is being defined. And phases are separated from each part of a system by definite phase boundary. So remember back, if you see over here, okay, so you see there's a line, right? So this is actually the phase boundary, okay, sempadan fasa, that actually separates different phase. You have solid, liquid, so it is actually separated by a boundary, sempadan. So this actually we call it as phase boundary. And for a single phase system, we normally refer it as homogeneous phase. Two or more phase system, then we call it as heterogeneous phase. If you have two components, meaning that you produce alloy, you ada, for example, carbon steel, you ada iron and also carbon. So this actually produce a so-called binary. Binary, it means that two components. And if let's say that you have more than three components, uh, for example, three we call it as ternary phase diagram. Okay, I need to admit others. Maybe some is still waiting. All right. Okay. And then we also have component. Okay, so component actually defined as a chemically recognized species. For example, if you have carbon steel, then you know that the component will be iron and carbon. Sekejap, admit lagi. Alright, and if you have solder wire, soldering materials, you know that it is actually made of tin and also lead. Tin, Sn. Sn is actually stannum or tin, and Pb is actually lead or plumbum. Right? So the same, I think, definition as mentioned earlier, component, means that the element or compounds which are mixed initially. We also have phases. So phases actually means that the typical physical and chemically distinct materials. Okay, and you have these examples, aluminum, copper alloy. So this alloy is actually made from these two components, aluminum and copper. So when it is infused together, so the basic principle how you are going to prepare alloy is that you need to melt the individual metal. You melt aluminum and you melt copper. So once it is actually exists as a molten condition, liquid, then you mix. So when you mix, you let it cool and it will become solidified. So there's a few characters that you need to follow in order to produce a homogeneous alloy. But if it is not homogeneous, meaning that the characteristic of each component is not the same, then it will produce eutectic alloy and whatsoever. Okay. So before we discuss further about the requirement, how you actually wanted to produce alloy, maybe we can look into the Gibbs phase rule. So in the Gibbs phase rule, it actually explained that the equilibrium between phases is influenced by temperature, pressure, and concentration. So if actually you change the temperature, if you change the pressure, and if you change the composition or the concentration, you know that it will actually change the phase. Therefore, the number of degree of freedom, F, is related to the number of component and phases, P. So you have these two rules, okay, in order to calculate the phase Gibbs rule. So F is equal to C minus P plus 2, where pressure and temperature can be changed. Or you have another formula, F is equals to C minus P plus 1, where the pressure and temperature is constant. All right. So looking at the effect of temperature and composition. So we are going to look at a very simple example. Okay. Macam mana nak buat air sirap ataupun how you are going to prepare sugary drinks. Okay. You have to understand that by changing the temperature, it will change the number of phases. This is actually always true. If you change the temperature, let's say that if you increase the temperature up to 100 degree, then you know that the liquid will be changed into vapor or gas. If the temperature is being changed, okay, to 0 degree, then you know that the liquid will be solid. So this is actually the meaning of this first point. Second point, changing the composition can change the number of phases too. So the component, for example, over here, if you want to prepare water sugar system, so the x-axis actually indicates the composition of sugar. You have 0. 0 means no sugar. Coke 0. Itu no sugar. Okay. So you have a different percent weight of sugar, 20, 40, 60, 70, 80, and 100. 100 means that all actually total sugar lah. So you can see from here, as you increase the percent of composition of sugar, what happened is basically, okay, the liquid solution will become thicker. Ini you masukkan apa tu gula kat dalam air. So and then at the same time you increase the temperature. You will see that this is actually the phase. It will be in liquid, okay, up to this temperature. But if you increase beyond 60% of sugar, then you will see that it will be a composition between liquid and also solid. Most of the liquid will be evaporate because you increase the temperature. So when it become evaporate, the sugar will become recrystallize. So it will become crystal, then it will become solid. So that is why you have one phase that will be known as a mixture phases between liquid and also solid. Okay. And finally, if you heat it, I think up to 100 degree, then most of the liquid will be vaporized. Then the content inside the container or the beaker will be only sugar. All right. So phase diagram, as I said, this is actually a very simple isomorphous system. What does it mean by isomorphous? Can anyone tell? Sekejap, nak kena admit lagi orang. Okay. Right. So what does it mean by isomorphous? Okay. Right. So isomorphous, mana pen saya ni? Okay, here. Isomorphous actually means that this is homogeneous. Homogeneous system. So you have phase diagram of copper nickel isomorphous system. So this is a very classical or very general phase diagram of a homogeneous system or isomorphous system. So in this course, for KIT 257, you will learn about binary system, which means that you will learn about just two components, and at the same time, it will be independent variables. So temperature and also composition that we always consider. So we are not looking at pressure or other things. Okay, normally it's just temperature versus composition. All right. So in order to understand this phase diagram, you will see that from 1600, okay, and from the composition 0 up until 100% of nickel. So 100% of nickel, it means that this is actually 100% of what? Anyone knows? Copper. Okay, because you are actually mixing copper and nickel. So when 0% of nickel, it means that 100% of copper. 20% of nickel, it means that 80% of copper. 40% of nickel, it means that the remaining 60% is copper, blah, 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 until over here, you have 100% of nickel or it is actually equals to 0% of copper, right? So from here, you can actually easily read. For example, if I put A over here, okay, A over there, composition, okay, of A, let's say we are referring to this phase diagram and I put A, okay. So we know that A actually has 20% of nickel and 80% of copper, but I just write it as 20% of nickel. So if I ask you at 1400 degrees C, what will be the phase? Siapa boleh jawab? Saya belanja coki-coki. 1400. Okay. At 1400 at point A. So what will be the phase? Ni kacang je punya soalan ni. You can write in the chat box. Or do you want me to call names? I can. Nurul Syafiqah. Nurul Syafiqah apa ni? Syafiqah Syarudin. Ada tak? Syafiqah Syarudin. Masuk. Nurul Syafiqah. Diam je. Okay. Oh, I changed to another person. Alicia, yo. Alicia, are you there?
Yes.
Yes. So what would be the answer? What is actually the phase of point A at the composition of 20% and at 1400 degrees C? What is the phase?
Liquid phase.
Liquid. Confident?
Yes.
Confident. Okay. All right. Maybe I ask another person. Cassandra Chiu. Cassandra, are you there?
Yes, doctor.
Okay. So what would be the phase?
Liquid.
Liquid. Confident?
Yeah.
Okay. All right. So good. I guess you are paying attention. Okay. All right. So how did you know it is actually liquid? Very simple. Because you see that A is located at this region. The green one, it is located in liquid region. So anywhere, if I put Syafiqah kat sini. Syafiqah sebab dia tak ada, saya panggil tak jawab. Syafiqah kat sini. At composition of 80% and at the temperature of 1500, still the phase will be liquid. If I put point B over here, okay, at the composition of 60, probably at 1300, okay, so what will be the phase? Siapa boleh jawab? Point B. Hana Atirah ada tak? Hana Atirah masuk. Tak ada juga. Oh, ni nak kena letak nama ni dekat dalam ni. Okey, Kamala Veni. Kamala Veni. Still missing. Okey. Alright. Siapa yang tak ada ni memang I actually assume you are absent lah. Okey. Nur Raihan. Raihan ada, Raihan?
Ya, ada.
Ada. Okay. So point B. What is the phase? Tahu tak tahu? Boleh teka je lah. Agak-agak apa?
Tak tahu.
Tak tahu? Agak-agak
Tak
point
tahu.
B tu dia ada dekat mana? Region mana?
Dia antara solid dengan liquid.
Okay. Nampak B tu? I think you can see B is actually located at white region, right? Putih tu. Kan? Nampak tak? Dia dalam region yang putih, So white region over there, it is mentioned L plus alpha, liquid plus alpha. Okay, alpha is actually solid lah. So you have a region of liquid plus solid. So point B, you know that at 60% of nickel, okay, at 1300, okay, so phase will be liquid plus alpha, okay, or liquid plus solid. Boleh? Alright. So, if let's say that you have another composition, tadi saya panggil siapa? Kamala, Kamala kat sini. Okay, 40%. At 1100, what will be the phase? The phase will be alpha or solid, because it is actually in this region, blue region. Anything that is fall into this range will be known as alpha or solid. Anything that fall into this region, white region, will be known as liquid plus alpha, and anything that falls into the green region will be known as liquid. Okay, is it clear? All right, so back to the concept, binary isomorphous system. Okay, so how does it possible for an alloy to form isomorphous system or homogeneous? So a complete solubility of two components in another at a constant pressure. But why copper and nickel will show complete solubility? I guess this one you also have learned with Dr. Chua before. Okay, so I just want to test you lah. So you have copper and nickel. So when you mix these two, metals together, you melt copper and you melt nickel, you mix it together and it will produce this kind of phase diagram. Okay. Then how does it possible? Okay. So basically there's a rule that you need to follow. So anyone remember what does it, what is the form, the rules that you need to follow in order to achieve complete solubility? I think you learn with Dr. Chua in chapter 4 or what? Diffusion, something like that. Anyone still remember? What's the formula? Or what's the rule that you need to follow? Ui Kai Sian. Ui Kai Sian.
Yes, doctor, I'm here.
Yes. So what is the rule that you need to follow?
Hume Rothery rules.
Oh, correct. So if I stay beside you, I will give you 50 ringgit. So meaning that you can follow the lecture very well. Okay. So I think we have answered it correctly. Actually, in order to follow or to produce homogeneous system, okay, it needs to follow Hume Rothery rule. Okay, so anyone still remember what will be the main rules or main point in Hume Rothery rules? Number one. Okay, saya nak tanya Solawatul, Syifa. Solawatul ada, Solawatul?
Ada, doktor.
Okay, so what is actually the first point in this rule?
Saya tak ingat, doktor.
Okay.
Sorry.
Alright. It's okay. Never mind. Siti Najihah? Siti Najihah? Disappear. Okay. Tan Chin Kai. Tan Chin Kai, are you there? No, missing. Wong Wei Sheng. Wong Wei Sheng?
Yes, doctor.
Okay, right. So what would be the first point in Hume Rothery's rule? In order to achieve complete solubility, what do you need?
Their atomic radius should be similar, not more than 15%, less than 15%.
Okay, all right. Atomic radius, we are talking about the difference of atomic radius, not more than 50%. But normally I will put that as maybe a third point. The most important point in Hume Rothery is to have similar similar crystal structure. This is actually the most important thing. If the atomic radius is, the difference is not much, but the crystal structure is not the same, it is not going to produce isomorphous system. So always remember, the most important or the priority in Hume Rothery is to have similar crystal structure. For example, copper. You see, copper, it has FCC, face-centered cubic. Both are actually having the same face-centered cubic. All right. Second, what will be the next rules or points in Hume Rothery that you think it is important to achieve complete solubility? Saya nak tanya. So, Ishan, are you there?
Yes, doctor.
Yeah, okay. So, what will be the next point?
The electronegativity of the so atoms cannot be too large difference, but must similar electronegativity.
Electronegativity, But as I said, electronegativity also, I will put it as last point, because in Hume Rothery you will have at least four important points. Okay, so maybe we will say that electronegativity, and difference in atomic radius. Okay, so what is actually remaining? What do you think? You've learned this. Saya tanya, dia ada dua orang Syafiqah ni. So saya tanya, tadi saya lupa Syafiqah mana satu. Syafiqah Najah ada tak?
Ada, doktor.
Okay, alright. Takut dia tu. Okay, so Syafiqah Najah, apa tu? What is the remaining points?
Tak ingat, doktor.
Baru patah tak ingat. Okay. Alright. So, the remaining is actually the valency. Okay. Copper. What will be the valency of copper? Anyone knows? Copper, 2 plus. Nickel also 2 plus. Okay. So in order to follow Hume Rothery, normally I will set this as priority. First is to have similar crystal structure. Second is to have the similar valency, and the rest will be as follows. Difference in atomic radius, not more than 15%. And finally, electronegativity. Because sometimes electronegativity, if the value is not the same, but the first 3 points is followed, then automatically it will follow the Hume Rothery rules. Okay, it will achieve unlimited solid solubility. Okay, so it means that it dissolves. Unlimited solid solubility. If it didn't follow, then it will actually achieve limited solid solubility. Okay, so this is actually the reason why when you mix copper and nickel, okay, you will get isomorphous, because you have similar crystal structure, electronegativity, and difference of atomic radius, which is small, that promotes high mutual solubility. So this is actually the reason. Okay, so now we are looking at example 1. Determine the degree of freedom in copper 50% nickel alloy at A 1085 degrees C, B 1300, C 1450. Okay, so first you need to understand the question. The question asked was, what will be the degree of freedom at copper 50% of nickel? So from this phase diagram, copper nickel, okay, you just look at 50%. So I put dotted line here, 50%. So I draw a vertical line here, 50%. And first, they ask at 1085. So 1085 is somewhere here. Okay. Maybe I put here A lah. Okay. So phase. What will be the phase? Of course, here you will see that A is located at solid solution phase. So the phase will be solid. Okay. So what will be the degree of freedom? Okay. So we are using this formula. F is equals to, okay, C minus P plus 1. This is actually the formula that we are following. So, composition. Okay, so composition at point A. What will be the composition? Composition, you know that it is 50% of nickel and 50% of copper. Then you know that your composition you have 2 because you have 50% of nickel and 50% of copper. So you have 2 components. So component is actually equals to 2. Understood? P. Okay. So P, what be the phase? P is actually the phase lah. Okay. So phase, it will be solid solution. So you only have one, okay, phase. This is actually your phase lah, alpha or solid solution. FCC, SS, phase centered cubic solid solution. Then you put into the formula, substitute, C is equal to 2. 2 minus 1 is equal to 1. 1 plus 1 is equal to 2. Okay. All right. Next one. Okay. Degree of freedom at the temperature of 1300. Still at 50%. And at 1300. So this is actually the point. Okay. So let us indicate first. Phase. Okay. So the phases you have solid solution plus liquid. Because it is actually in this white region. So anything that falls into this white region, it will be SS plus L or liquid plus alpha. Okay. All right. So definitely for the phase, you know that it has 2 because it is a mixture. You have like liquid and also solid at the same time. Okay. So that is why phase over here, it mentioned you have 2. Composition still the same because it is at 50% of nickel, then still it is 2 because still 50% of nickel and 50% of copper. Right, then you can calculate degree of freedom, 2 minus 2 plus 1, so equal 1. Okay, get it? And then finally at point C, okay, still at 50% and at 1450 degrees C. So this is actually the point. You have point C. Phase is equals to liquid, fasa, liquid saja. So you have 1. Composition still 2 because it is still 50% of nickel, 50% of copper. So you substitute into the formula, 2 minus 1 plus 1 is equal to 2. Okay? Any questions so far? Ada soalan? Ada apa-apa nak tanya? Soalan? I think it's quite clear cut. Okay, so what does it mean by solid solution? Okay, so we've seen this, alpha, or solid solution. But what is it? Okay, so solid solution is actually a solid state solution of one or more solutes in a solvent. Often considered when the crystal structure of the solvent remains unchanged by addition of solute and when the mixture remains in a single homogeneous phase. The solute may incorporate into the solvent crystal lattice substitutionally or interstitially. Okay. The primary, there are 2 types of solid solution. You have substitutional or interstitial. So substitutional, it means that the solute atoms occupy the regular lattice. So dia substitute lah, dia bertukar ganti. Interstitial, it is actually means that the solute atoms occupy the interstitial position. It will actually exist in between the solute atoms. So this is actually the arrangement lah. So you have substitutional, it actually substitutes the position. So for example, you have red and blue. So red can actually replace blue, or blue can actually replace red. Interstitial, it means that it appears in between the lattice. Okay, so both of this type of solid solution can affect the properties of the material by distorting the crystal lattice and disrupting the physical and electrical homogeneity. Okay, some mixture will readily form solid solution over a range of concentration, while other mixture will not form solid solution. Okay, the propensity for any two substances to form a solid solution is complicated matter involving chemical, crystallographic, quantum properties of a substance in question. Right. We've talked about Hume Rothery rules before. Okay. Then I guess maybe we just go through this part. So Hume Rothery is actually a set of basic rules that describe the condition under which an element could dissolve in a metal, forming a solid solution. Okay, so there are two sets of rules. Okay, you have substitutional and interstitial solid solution, but most of the rules actually follow the same thing as I mentioned earlier. Okay, so you have to look into the difference of atomic radius, not more than 15%. Crystal structure must match, must be the same. Maximum solubility occurs when the solvent or solute have the same valency. And finally, the solute and solvent should have almost similar, not having totally similar, but almost similar electronegativity. But remember, as what I told you earlier, the importance, the priority for Hume Rothery rules, normally I will put the crystal structure first. Okay, second, valency. Third, okay, maybe difference of atomic radius. Okay, and fourth, it will be for the electronegativity. So if it actually follows first, second rules, or even up to third rule, then automatically we say that it follow Hume Rothery rules. Okay, all right. So maybe we can do this. Just look at this example, practice 1. Okay, based on Hume Rothery rules, which of the following system will be expected to display unlimited solid solution? Explain. So A, B, C, and D. Maybe with the time provided, we can do this. I guess for a while. Boleh tak saya nak bagi A ni? Siapa? Cari boy lah pula. Muhammad Syami. Muhammad Syami ada tak? Muhammad Syami. Say hi sikit. Syami. Tak ada Syami. Okay. Muhammad Uwais. Uwais ada Uwais?
Yes, betul.
Ada? Okay, cantik. Alright. So Uwais, cuba buat yang A Try lah. Kejap lagi kita tanya Uwais. Alright. Najwa Izani. Najwa Izani ada tak?
Ada, doktor.
Ada. Okay. Najwa Izani yang B. Okay. And then Natra. Natra ada? Natra Amira.
Ada, doktor.
Ada. Okay. Natra buat C. And finally, Adriana. Nur Adriana. Adriana ada? Adriana. Adriana tak ada. Okay. Adriana tidur kot. Alright. Adlina ada? Nur Adlina ada?
Ada, doktor.
Okay. Adlina yang last sekali. D. So, I give you 1 minute lah. Okay. Untuk tengok. Okay. The information over here. And you tell me whether this pairing, silver, iron, cobalt, iron, gold, silver, and magnesium, cadmium, does it actually display unlimited solid solubility? And if yes, explain why. So I think all the information are provided there. Okay, difference of atomic radius, crystal structure, okay, electronegativity, and also valency. Okay, Wise dah dapat dah, Wise. A. Boleh tak boleh? Wise. Rasa-rasanya. Does it forming Wise?
Yeah,
Boleh tak? Apa tu?
boleh.
If is it possible for silver and iron to form unlimited solid solubility? What do you think? Boleh ke tak?
Not really, because
Why?
according to Hume Rothery rules,
Mm-hmm.
because two different crystal structure.
Okay. Good. Okay.
And
And then?
if we calculate the ionic radius difference, is it okay? Because it count 0.16%.
Okay. Okay. All
Then
right.
the valency,
Does it match
so
valency?
no,
No. Okay. All right. So, as a conclusion, do you think that silver and iron will display unlimited solid solubility?
no,
No. Okay. So the reason is because
because they're different in the structure crystal
okay, good. I'm circling this one. And then what else?
different in valency.
Different in valency. Very good. Okay. So the answer is actually no. No, or it will actually show limited solid solution. Why? Because it has different crystal structure, and then it also have different valency. Normally, if you see these two things already not similar, automatically don't look others. So we know that, okay, it already didn't follow Hume Rothery rules. Even though, okay, you know that when you calculate the atomic radius, it is still small. Electronegativity is also close. But these two things actually didn't follow. So in order for you guys to answer in exams, it is always important not only to mention crystal structure and valency, not the same, that's all. But you also have to tell, okay, silver and iron will display limited solid solubility because, okay, first, the crystal structure for silver is face-centered cubic and crystal structure for iron is body-centered cubic. It is not the same. Second, it is actually due to the valency. Valency for silver is +1, and then valency for iron is +2. Okay. Nevertheless, the difference in atomic radius is still less than 15%, and the electronegativity is still almost similar. But I think looking into the priority rules, then it actually display limited solid solubility. Okay, tadi B tadi saya suruh siapa buat dah. B tadi siapa Natra ke Najwa?
Saya.
Najwa. Okay, Najwa. So macam mana Najwa? What do you think?
I think for the atomic size difference, this is the same. Because it has slightly difference.
Okay.
But for the crystal structure, for CO is HDP, meanwhile for the VE is BCC. It's not the
Okay.
same. For the electronegativity is same, and for the valency is also the same.
Okay. So what do you think? Is it going to produce unlimited or display unlimited solid solubility?
I think yes.
Yes. You think yes?
Yeah. Maybe.
Okay. So, anyone agree with that? Actually, the answer still will be no. it still cannot produce unlimited solid solubility, because, as I said, the priority rules in Hume Rothery is crystal structure. So even though I think the 3 points have I think successfully follow, but the most important one, crystal structure, it didn't follow. So still this one, it produce limited solid solution. Okay, Najwa,
Okay, Doctor.
Alright. So I think I would like to congratulate you lah for trying. So it's nothing wrong lah. I mean, we are learning. Okay. So Natra, Natra C kan? Betul tak?
Betul.
So macam mana, C boleh ke tak boleh?
Tak boleh. Saya
C
rasa
tak
tak
boleh.
boleh.
Okay. So
Sebab
why you say that is not possible?
electronegativity dia different quite huge. 0.6.
Okay. Electronegativity, anyone want to add that one? Siapa yang kata boleh? Ada yang kata boleh? Tak tahu? Okey. Atirah cakap boleh. Okay, so Atirah kata boleh. So, answer is actually yes, it can. So remember, I think I put electronegativity as the last requirement. Okay. So, here you will see that crystal structure, it's the same. FCC, FCC. Valency also the same. +1, +1. Difference in atomic radius, not much. Very small, 0.003. Okay. So still less, okay, than 15. And how about the electronegativity? Electronegativity 2.5 and 1.9. Actually, the difference, even though there's a difference, clear difference, 0.4 difference, but as I said, electronegativity, normally I will put it as the last requirement. If it follows the first three, then we will say that it will follow Hume Rothery rules. Okay, so we still see that 2.5 and 1.9 is considered almost the same, still almost the same. So this actually will produce unlimited solid solution. Okay, last one before we end our lecture. Okay, last one. Siapa tadi saya suruh buat tadi? Atirah Ke siapa? Adlina?
Adlina.
Okay, Adlina. Yes, Adlina. Silakan. Boleh tak boleh?
Boleh.
Boleh.
Because crystal structure the same.
Okay.
Then valency also same.
Valency same. Okay.
And
Atomic
then
radius? Atomic radius?
atomic radius
Kira tak?
beza dia sikit je.
Beza dia sikit je.
So
So still
boleh.
boleh. Dapat berapa atomic radius? Ada kira ke? Tak ada.
Beza dia 0.01.
0.01. Ada cari dia punya persen tak? You can actually refer to this formula lah if you want to calculate. Okay. So whether you know
7 point something.
11.
7 point something.
7 point something lah. 7%. Okay. So those who need to ask like how we actually calculate the formula for atomic radius, you have solute and also solvent. So which one will be solvent, which one will be solute? So solvent is actually solute will be the one that is bigger in size. Okay. Macam yang ni 0.16 ni solute lah, and the smaller size will be the solvent. 0.149 will be the solvent. So you get this difference and you divide with 0.149, then you will get 7%. Okay, so for this one, the answer is also yes, can. Okay, unlimited solid solution. Okay, all right. So I guess the explanation, I think everything is here. Then this is just example lah for A, but the rest we already discussed. So tomorrow we are going to look into how we are going to interpret isomorphous phase diagram. Okay. And before I end the lecture, is there anything that you would like to ask? Ada apa-apa soalan nak tanya? Make sure that you scan the QR code, okay, for your attendance. Okay. Kalau ada soalan, can ask in the chat box. But if there's no further question, then I will adjourn our lecture today. So it has been wonderful to have a discussion with you guys. So looking forward to meet you tomorrow. Okay. And inshallah be ready, because I think my lecture anytime I will do quiz. So make sure that you always revise your work, okay, your lesson. So with that, thank you very much. I'll see you tomorrow. Assalamualaikum warahmatullahi wabarakatuh. Goodbye, everyone.